but they just won't be in class. The exam is in class, closed book, and you know the syllabus, it covers everything from after the midterm. I posted a review document on Canvas. This is mostly a collection of items that I expect you to be aware of. This can kind of help you guide your study. I don't want to, I was telling my TAs yesterday, I don't want to post a practice final exam, because in some sense the practice final exam is basically a list of questions that won't show up in the exam. So I really don't see a point to that, and I'm more interested in guiding you through what you need to know rather than what you need to do to get get something in the exam. Questions about the exam? Okay, everyone looks excited. There's a project report that's due on the 15th of December. Please upload it to Canvas. And this is, it should be a short document, no more than 6 pages, that describes what you did in the project, how it went, any experience that you have. If you have more time, how would you continue with the project, what the project taught you about machine learning, what you applied from class, how that connects to the class, and also some of the details of how you implemented things. Most of you are doing something experimental, so how you implemented things, any details of difficulties that you face with implementation, and you might also want to mention any related work that you came across that is connected to this project. Those of you who are doing a competitive project, just continue what you did for the intermediate report, but expand it to 6 algorithms. Again, just to remind you, any algorithm that we covered in class, I expect that you have implemented it, and you should be also posting, uploading stuff on Canvas, not Canvas, on Kaggle, so that you you're ranked somewhere. I'm not going to really consider your ranking into the grading. I'm more interested in knowing that you did all the right stuff. Yes?
So we don't need to submit a paper for...
No, you need to do both.
Okay, we do.
Yes, because the competitive project, your evaluation is only via Kaggle. You might have your own internal evaluation, but your actual evaluation is via Kaggle. So in your report, you can also mention where you stand in the rankings at the time of submission. And, or not, I don't care. More importantly, please don't put it away till the last minute. Get it done. I mean, if you remember that the project reports are actually due tomorrow, and many of you promised that you'll have the project reports tomorrow. So I don't want to disappoint you, so you're welcome to upload it. Any questions about the final or the project? Those of you who came in late, just two announcements. There's a final on the 14th. The project reports. The project reports are due on the 15th.
What's the time limit on the exam?
Does anyone know? I think 3 hours. Is it?
2 hours.
2 hours. Okay, 2 hours. Yeah, right. 2 hours. 3 hours is too long for me. Yes.
So in the review document, I mean, there's a lot in there. It's wonderful. That's sarcastic. But so that's not everything that we've covered, though. So would you say that if we on the basis of this review document, we're good to go?
What is not there in the review document that we covered?
Well, you don't. So, for example, you didn't put the title of every slide, just most slides.
It's mostly the concepts. It's the concepts. I think I would argue that in order to understand the review document and be comfortable about it, you need to know everything that we covered.
Okay.
So it's not that this is all that is needed to, say, for instance, do machine learning. So, in fact, I have a slide later today about that talks exactly about that. So, it's not the title of every slide. You will see the title of many slides, but I think in order to understand those things, you'll have to, maybe look at the previous and the next slide as well. Alright, one other announcement. Early January, on Jan 13th, we have a campus-wide celebration of data science. It's the first ever Utah Data Science Day, and we are hoping to make this an annual event. It's on Jan 13th. It's going to have a bunch of invited talks. Actually, one keynote talk by this person from Amazon who does machine learning. 4 people from around campus who apply data science in their own research. There's going to be a job fair with local companies. There's going to be a panel discussion about data science and the industry. And from your perspective, there's going to be a poster or demo session where people from campus can present their research or anything that they are doing with respect to data science. And some of you are actually, some of you came to me asking whether they can present their class project as a poster. If you feel particularly excited or happy about it and you want to share it to the world, then why not? If you think that you're doing something that it might help the rest of the world to know about, why not? This is a campus-wide event, so you might want to consider signing up for the poster. There's a URL there, you can check it out. It's fairly easy to remember, datascience.utah.edu. Yes?
Turning back to the exam really quickly.
Okay?
So I see we have solutions for the theory part of like 1, 2, and 4. Are you going to post solutions for the other homeworks or no? Or can you?
Oh yeah, we will.
Okay, awesome.
I've asked my TS to finish grading homework 5 this weekend. We'll post solutions for all the homeworks. We can do it now, right? We can post all of it.
Okay.
Yeah. And of course 3 you already have the solutions. Because they were all the questions were on campus.
Yes.
So
yes.
you will have all the homework solutions soon.
Okay.
Hopefully even today. Other questions? Okay, so let's move to the final lecture. And I like taking this opportunity, the final lecture, to kind of talk about some practical aspects of how machine learning might be applied. So this is a combination of ideas and opinions that are mine, as well as opinions that have been put forth by other people who do both applied and core machine learning. So this lecture is all about making machine learning work in the real world. And if you want to know more about this, there's actually a ton of stuff that's out there. People have written about this, and there are readings on the class website that you might want to consider. And as with everything machine learning, take everything with a pinch of salt. So I want to cover 3 topics today. One is a question that many people have asked me in the class. How do you diagnose your ML algorithms? How do you diagnose so let's say you've trained a classifier and it's not working. It's not working according to whatever measure that you care about. What do you do? How do you debug a machine learning problem? That's the internal debugging. The classifier is not working, how do you make it work? And then, let's say you've thrown everything you know at it. How do you do, I'm going to talk about the importance of error analysis, analyzing the mistakes that your classifier makes for 2 reasons. And this is important for 2 reasons. One, it will give you a better understanding of what your classifier does. And 2, it will prevent you from making any false claims. And I'm going to wind up this thing talking about how do you inject machine learning into something that you want to build next. Alright, let's talk about diagnostics. So let's say you've trained a spam detector and you've used SVM or logistic regression or whatever you want. And you've done all the right things. You've used cross-validation, for example, to find all the hyperparameters, and you evaluate on a pristine data set that neither you nor your classifier has seen before, and you only get 75% accuracy. And 75 is not good, let's say, for this task. What do? Ideas? You've already, go ahead.
Try adding a nonlinear kernel.
You can try non-linearity. Okay, that's one idea. Anything else?
Maybe finding the outlier.
Finding the outliers. Anything else?
Examine your features.
Examine your features. And one more maybe, and then we can move. Yes? Sorry? Ensembles. You get a more complex classifier. So, when I thought about this, I came up with at least 3 different ideas. You can use more training data. We know from learning theory that more data is a good thing in general. So you can use more training data. You can play with your features. You can use more features or less features or other features. You can do better training, use a different algorithm, run for more iterations, use, train a different model, like an ensemble or a nonlinear classifier. You can tweak the regularizer. And there are so many different things that you can do to make your classifier better. The problem with this is the search space is so large. Now, the search space is the search space over tweaks. And unfortunately, it seems like this is a process that's dependent on which side of the bed you wake up on. It's a random process, and one thing I want to kind of talk about is how do you make the search over these kinds of ideas more methodical. In order to do that, you need to first diagnose where your problems are. You need to know what is causing the problem before you even start to fix it. And from the entire semester, we know that there are a few ways in which your classifier can be wrong. Your classifier could be overfitting your training data. In other words, your classifier might have high variance. Your classifier could be underfitting your training data, which means that your hypothesis space has high bias. Your learning algorithm does not converge. Maybe you implemented a learner, it does some optimization, it's not converging. Or perhaps you've implemented a learner by optimizing a loss function, and it just so happens that the loss function you've chosen does not reflect real life. Let's try to go through this list and try to identify how to diagnose these various situations. And I'm not going to give you, clear answers. I'm just going to give you hints. Debugging is an art, and debugging machine learning is almost a black art. So let's talk about over and underfitting. Just to remind you, overfitting is a situation where your training accuracy is much higher than the test or generalization accuracy. And what this means is your model is able to explain the training set very well, but you've ended up with a classifier that really does not generalize to future examples. And if you remember, learning is all about generalization, so overfitting is poisonous. Underfitting is the situation where both training and generalization accuracies are low, which means your hypothesis space that you've chosen is poor, and it cannot represent the true concept. So how do you detect overfitting and underfitting? One way of doing that is to plot the training and generalization error as you increase as you add more and more training examples. So you might have a training set, you start off with a small subset, calculate the training error, the generalization error, and do the same thing for more and more. Typically what will happen is your training error might look something like this. When you have very little training data at somewhere around here, you see that your training error might actually be very low. Why? Because we have very few examples and you ended up overfitting. You have like 3 examples, your classifier ends up remembering those 3 examples and it does very well on that, so probably it has very low error. As you add more training data, your training error might go up, which seems counterintuitive. As you add more training data, your training error might go up because finally you are allowing your model to reconcile with the fact that your data might not be self-consistent, for example. I'm not saying this will always happen, but this can happen. So, does that make sense? Any questions about that? We've still not talked about how to detect overfitting. At the same time, you plot the test error or the generalization error, which means you have a held out data set and you plot the error of the classifier on that held out data set as the training set increases. Typically what happens is the generalization error goes down. Why? Because you have more data, and we know from all our analysis of learning theory and all that more data leads to better generalization. That's fine, but a classic symptom of overfitting is when there is permanently a large gap between the training error and the generalization error. So if it seems like your training error is converging to here, or generalization error is converging here, and your training error is converging here, that suggests that you're overfitting your training set. Of course, eventually, this is not entirely the right picture. Eventually, if you have infinite training data, you have ended up overfitting. And overfitting is not a bad thing, because if you have seen every possible example, then getting the right answer on every possible example is probably a good thing. But we are not in the regime of infinite data, so if you see an unacceptable gap between training and generalization error, you might end up, it might be a sign that you're overfitting. Underfitting is a situation where both training and test error converge to something that's unacceptable. So the errors are high, both even on the training set. If even the training error is high, that means the hypothesis space that you've chosen is not good enough to represent the complexity of the task that you're dealing with. Okay? Questions? And this is something that you can do independent of what your learning algorithm is. You can write code that spits out these curves no matter what learning algorithms use, and use this as a diagnostic for any new task that you have. Now, what this tells you is if you're overfitting, you probably need more training data. Because as you notice, if you're overfitting, more training data is better. If you're underfitting, you probably need more features. If you're overfitting, you probably need fewer features. If you are overfitting or underfitting, maybe changing features will help. That's why I said it's a bit of an art. Playing with regularization is another way of controlling overfitting and underfitting. Remember, for things like SVMs, if you increase C, you end up overfitting. If you decrease C, you end up underfitting. So playing with that regularization constant or the trade-off parameter might be a way of controlling overfitting or underfitting. If you notice that you're overfitting, you probably want to decrease that C value. Alright. Let's say there's another way of diagnosing problems is to look at the convergence of your learning. So, if a dominant way of thinking about learning is to frame it as an optimization problem, learning as loss minimization. If you're minimizing a loss, or if you're minimizing any objective function, you can plot the objective with as the number of iterations goes. And this is what you did in your homework. And typically, if you're minimizing, you'll see a curve that looks like this. And if you see a curve that looks like this, you can identify distinct regimes. There is some area, there's some number of iterations before which you can say, you know what, the objective is still decreasing. So learning is not yet complete. After a certain point, you can say that the decrease is very low. From here to here, say from here to here, the decrease is really small. And you can say, at this point I'm going to declare that learning is done, it's converged. So this can be a way of identifying whether you need to run for more iterations. That's nice, but it's not always easy to decide. So it's clear that in this area learning is not complete, but it seems like it's still decreasing here, and sometimes you'll see situations where even after running for thousands of iterations, the objective keeps decreasing, at which point you have to decide how, are you happy enough with, you have a budget of computation, you don't have more time to bring out, produce a better model, you decide to stop. So at this point, practical consideration is taken. But one thing that you know for sure is if you're minimizing a function and you're doing something like a gradient descent, something's wrong if your objective, if your learning curve looks like this. If it keeps going up and down in a crazy way. Because you're minimizing a function. You're doing gradient descent to go down the gradient of a function. And that means the objective should not really increase. Because mathematically, you can show that going down the gradient should decrease the value of the objective. If it behaves like this, that means something's wrong with your learning rate, for example, or something's wrong with your update, something might be wrong with your gradient. And these are the more insidious bugs to fix. That's it for stochastic gradient descent. You will find that your objective ends up wobbling quite a bit, especially in the beginning. So you should account for a little bit of wobble, but not extreme variance. Questions? Yes.
So is there something called feature scaling to help with?
Feature scaling is very useful. It's a way of transforming your features so that it does not help with what do you call this? With optimization. With respect to optimization, this is just an optimization problem. It does not really care that you're doing machine learning. But feature scaling is useful often when maybe I mentioned this example where you have height and weight, and your height's in grams. So clearly one feature will dominate the other. So in that situation, you might want to normalize your features. How do you normalize your features? Again, that's a design choice. Detect that your features are poorly scaled is to just observe the variance of each feature. If it seems like the variance of each feature is extremely, if the variances are very widely spread out, that means that one feature has the potential to dominate the search. So that's one thing that you can do. In fact, I should probably have a slide about that. One way of doing feature scaling, for example, is to do some sort of, you can transform your features by subtracting the mean and dividing by the standard deviation, for example. Or subtracting the minimum and dividing by the range. This will put all features in the range of 0 to 1, for instance. Other questions? Okay, so if you know that your learning has not converged, you can run for more iterations. If you know that your algorithm is not working, in order to know whether your algorithm learning is actually working or not, you should always track the objective that you are optimizing. And this is what you did in your last homework. Because that's, in some sense, a basic check that will let you know whether something terribly wrong is happening or not. Typically what will happen is you will use a library that does your optimization for you, and at that point you're putting your trust on the person who wrote or the people who wrote the library to do your optimization for you. And more often than not, they end up doing a reasonable job, but it's always good to look at the objective, because even if you are using an optimization library, you might sometimes have to write your own gradient, and as you know, deriving and implementing gradients is not fun. Alright, so the other problem is it's possible that your loss function is not good enough. Remember, if I want to build a classifier, the best optimum thing to do is to minimize the 0-1 loss. And minimizing the 0-1 loss is intractable, so we have to keep inventing surrogates like the hinge loss or the log loss, which is what the loss function for logistic regression is called. And sometimes, and this is not all that common, but sometimes your loss function might not accurately reflect the problem. I'll give you an example. Let's say you want to decide whether SVM is better or logistic regression is better for a problem. So let's say you have two different objectives, SVM and logistic regression, or more generally A and B. Now, I want to know whether which one is better suited for this particular task, say for spam detection, using your set of features. What you can do is train both the classifiers to convergence, and in general it doesn't matter what the objective is, in both cases we are minimizing the objective, which means lower is better. But you cannot compare the two different objectives because they are different functions. They are really not comparable with each other. All we know is that for SVM, a lower objective is better than a higher objective. For logistic regression, a lower objective is better than a higher objective. But after convergence, let's just say that the optimum, according to, if you know that the optimum value of the best objective value, best that you can hope to get to is 0. because zero, the objective in some sense talks about loss. So the best objective you can hope to get to is 0, and let's say it just so happens that the optimum value for objective A, let's say for SVM, is more than the optimum for B, which in a weak sense says that the objective B is better, whatever the classifier was. But it just so happens that the generalization error, the test error of A is better. Okay? What this means is that internally it looks like B is a better objective to capture the problem, but externally, from the point of view of generalization, A is better. This means that B does not capture the problem well enough. This is one way of knowing whether you should use SVM or logistic regression. This is generally true, but in practice, to be honest, I have hardly ever found a difference between these things. So between things like SVM and logistic regression, there's often a difference between, say, SVM, logistic regression, and something like perceptron if you do not use averaging. But what is a bit of a surprising fact is that typically many of these algorithms roughly do as well as the others, as each other. There's an equivalence class of in terms of performance, and this is a very loose statement. It's not a formal statement in any sense. The best algorithms all roughly do equivalently. You can't squeeze more out of the data just because you change your algorithm, if you come to a good enough algorithm. And which is why when you see papers in application domains, for example, say in natural language processing, people focus more on the application. They say, we trained a classifier for, say, predicting the sentiment of this sentence. And somewhere in a footnote, we used a logistic regression classifier. It's often like a footnote. And they used logistic regression because they had the source code for it and they had the infrastructure set up. Not because they had any strong philosophical reasons. If you have strong philosophical reasons about this, then you should be doing research in these things and trying to prove this is better than the other. That said, in general, one thing that I have noticed is that if you care about predicting just a label, discriminative models tend to perform better than generative ones. So for example, logistic regression invariably does better than naive Bayes, even though they have the same posterior distribution. Questions? And as I'm going through this, I want you to think about all the pains that you had to go through for your project and also for your homeworks. Because in some sense, you probably have faced all of these things. Maybe not exactly this one in any of your homeworks, but your objective not converging, or this sinking feeling that your features are just not good enough. There's the data set that you guys had for the SVM homework where everyone got like 58 or something, 58% accuracy, and it was, I must confess, disappointing. But such is life. And at some level, you need to be able to realize whether it's a fault of your implementation or if that's all there is in the problem. And these are kinds of tricks that might help you make that judgment. Alright, yes?
Sorry, you just mentioned that was disappointing. What accuracy were you hoping to see?
Oh no, I know that I was getting, when I ran an SVM on that data set, I got roughly the same as what you guys got. I can tell you what the data set was though. It's possible to get 100% on that if you knew which 5 of the 500 features were relevant. Turns out only 5 of them were relevant. So there was massive amounts of noise. So the features were, the data set was constructed to be adversarial, to be, as a challenge, this was from 2003, as a challenge for feature selection. And it was a perfect kind of a dirty data set to give you guys. That's what will happen when you apply machine learning in real life. You have no guarantee that your data is good. So let me talk about a different kind of error analysis, which is error analysis from the bigger application perspective. For this class, we've been looking at machine learning as the center of attention. You have your machine learning code, but in practice, It's a tiny, tiny, tiny part of a much larger application. You have to collect data, you have to do feature extraction, you have to do some resource management, verify that your data is right. You might have some infrastructure that wraps all of this around, and this is just one set of boxes, none of which I'm entirely familiar. At least half of them I'm not sure what they do, but I'm told that in the industry these kinds of boxes exist. And in the context of a large application, often the machine learning component is a tiny but probably very important piece. And you should keep that in mind. I would like to say that ML is the center of the world, but you know and I know that's not true. It's often a tiny piece, an important piece, or an increasingly important piece in a much larger application. So when you're doing any kind of error analysis for an application that uses machine learning, you should keep the context in mind. So there might be pre-processing of your data, which is not part of the machine learning algorithm. We never spoke about pre-processing. There might be feature extraction. There might be information that you, as say a domain expert, brings in. So this class represents a rather broad spectrum of people from across campus, and some of you are not from CS. You bring in information about a particular domain that I'm probably not even familiar with. So as a domain expert, you might know more about your problem, or you might hire a domain expert who knows more about your problem than someone who just looks at the mathematical underpinnings of machine learning. So my suggestion is always use any sort of domain knowledge that you have to help guide your learning, to help make your learning better. And this kind of domain knowledge can play a role in, say, data transformation, in feature selection, in feature generation, in defining the feature functions. And in addition to contributing to all these factors, each of these pieces of information that hopefully guide your learning might also contribute to the error. And one important question is, where do each of these pieces, how much of the error is brought into the game by each of these pieces? And it's important to keep that in mind and try to think of your ML machine learning driven application in the context of the larger system. So let me give you an example. Something that I'm particularly familiar with in the context of text processing. A typical text processing pipeline might look like this. You start off with some text, let's say a news article from New York Times, and you chop it up into words. And this is often, at least for English, this is often just a bunch of regular expressions. There's no machine learning here. So you can think of it as pre-processing. And then you use the original text and the words and train a classifier maybe to identify its parts of speech. And then you use the original text and the words and the parts of speech to build parse trees for all the sentences in the language. And then you use the original text and the parts of the words and the part of speech and the parse trees to build an application that does something, and each of these pieces from all the way from here, everything below, could be ML driven. Notice, so what's the problem? What's the classic problem with this kind of a situation? Yes?
Your error grows each time.
Exactly. If the part of speech tagger is 90% accurate, the parser is 90% accurate, and this thing is 90% accurate, then the error multiplies. So which means that your final application in this pipeline might be pretty lousy. But how do you know which subsystem to blame? One way of doing that is, does that make sense? If each of these are error prone, then your final answer is going to be, your final application is going to be pretty bad. In the context of this class, for example, we were only looking at something like this and pretending that everything that came before that was perfect. But that's clearly never going to happen. So one way of, one question that you should try to keep in mind always is, how much do the pre-processing steps contribute to the final error? And this can be done in one way of doing that is, suppose you knew the ground truth for the previous pieces. You plug in the ground truth and ask, what happens when you replace the predicted system of the pre-processing with the ground truth. So for instance, you can suppose in that picture that I had, the end-to-end system had a 55% accuracy. And you replace the piece that takes the text and converts it to words with ground truth words that, maybe a human actually wrote down. And let's say the accuracy goes up from 55 to 60%. This means the error in the words contributes to 5% of the total error. And then you could replace it with ground truth parts of speech and the ground truth words. And let's say the error goes up to 84% from 60. This means a huge part of the error, total final error, comes because your part of speech tagger was bad. Not because your final system was bad, but because your part of speech was bad. This is an indication that you probably need to replace it, or maybe you need to start doing research on that. And then let's say you replace it with ground truth parts trees, that could give you another 5% increase. And the final output, having everything ground truth except for the final thing, is only 11% away. So your classifier itself is not bad. It just so happens that your pre-processing is really, really bad, which is why the total system is only getting 55% accuracy. And this is true for natural language processing. This is true for pretty much every application of machine learning, especially now when we are getting to a situation where classifiers are creating features for other classifiers. And this is especially, and this might be true, for example, when your features are coming from sensors in the real world. So let's say you want to decide something about when a person wakes up based on their heart rate that's measured using, say, a device that they're wearing, based on some accelerometer and a bunch of sensors. And let's say each of these sensors, for whatever reason, are optimized to work in certain situations. Let's say all these sensors work at sea level in California in the kind of peculiar weather that the Bay Area has. And now you bring that entire system to Salt Lake City, it's at an elevation, it's dry, and maybe the sensors are not that good. So it's possible that your final error may not be because of the classifier that you're using, but because of the sensors. So how do you know that? What you have to do in this situation is take your entire system to California, pretend that your sensors are perfect, and then try to get the error. And that will tell you how much of the problem is yours and how much of the problem is somebody else's. And this is shockingly often forgotten. So another sort of study that you might want to do, and actually this is often useful to know how much a complicated machine learning idea is useful, is called a ablative study. This is used to explain the difference between a complex or a strong model and a much weaker one. The much weaker one, let's call it a baseline. This is usually done in the context of features. So let's say you have a collection of features that are all that you have painstakingly chosen and they all do a great job, but you don't. It's important to know, from the data science perspective, it's important to know not just that the system works, but why the system works. Which of these carefully chosen features are helping the most? And so you do an ablative study where you remove a few features at a time and retrain the system, and you see which one leads to the best increase in accuracy. And that's a way of knowing, in some sense, that's a way of understanding the data. It's going beyond just making a prediction and trying to understand what part of the input signal is actually most helpful. Yes?
Don't we calculate the information gain?
You could do something like that. But this is useful in the context of an end-to-end system. The information gain is again too local and too close to the data itself. This is in the context of the full system and all the slips, all the noise and everything from the rest of the system in place. And information gain in some sense is a greedy heuristic. It only picks one feature and says how much is it, how well does it predict the label. This is in the context of the entire system and your learning algorithm, your optimization error and everything like that. You have a question?
Yes. Will this be
would automatic relevance detection be an applicable study, or
Would what?
automatic relevance detection?
What does that mean?
It, I understand that it's used in the context of like Bayesian optimization and what I understand is that it tends to prefer fewer features.
Oh, sure. Yeah. So in general, there's always a push for preferring fewer features. If only you knew which few features to take, right? So feature selection is a part of this, but not all of it. For the same answer that I gave before, all of that happens within the learning algorithm. This is in the context of the system, and it's useful to know what's going on in the entire system. Very often, some of the best papers I read ends up having an entire section devoted to error analysis and ablation. Partly because that tells you not about the application, not about the internals of a machine learning algorithm, but about the task. And quite often you care about the task, not so much about whether you get to within epsilon or half of epsilon of the optimum possible objective. So it's always good to keep the broader context in mind and the entire sequence of all the noisy things that we are doing. Yes.
And for feature selection, is there a way to use statistics to, let's say, correlation between a feature and the...
There are actually multiple ways of doing this. In the worst case, this is an intractable problem. But everything that we know consists of heuristics. One way of doing feature selection, it's also called model selection, because if you change the features, you change the model. One way of doing model selection is playing with the regularizer. You can think of the regularizer as a way of automatically selecting features, because it penalizes adding extra features because it adds adding a non-zero weight. Right? A regularizer is a function that penalizes complexity. And complexity, one way of thinking about complexity is adding extra features. So one regularizer that does sort of push for sparse features is the L1 norm. All the regularizers we've looked at in the class are the L2 norm. So W transpose W. So it's a squared L2 norm. Instead of that, if you use the L1 norm and run the optimization, it tends to push for sparse features, and basically it zeroes out irrelevant features, or at least that's the hope. Another way of doing feature selection is something like this. You start off with the full selection of features, and somehow you use information theoretic criterion or some other criterion to decide, this one is the least interesting feature, let me throw this out and train a classifier. And you greedily go from, you pick increasingly more smaller subsets. Another way of doing that is to greedily grow increasingly larger subsets. There was an entire edition of the Journal for Machine Learning Research from 2003 devoted to feature selection. And the answer there was, there are 800 things you can try, but and it's not always clear what's the best thing to do. So it comes with experience, and that's again where domain knowledge is important. If you believe that your domain needs this one feature, and for whatever reason your learning algorithm is not picking up on it, it could mean one of two things. One, you're wrong, or two, it needs that feature, but it just so happens that the other features are compensating well enough that it's not picking up this feature, possibly. So there's a bit of an art in deciding all these things. Did you have a question? No? No? Okay, if you are confused, then no. Alright, so in the time that's left, I want to talk about how the kinds of things that you might have to do to inject machine learning into your task, some task that you care about. And let's say the task that you care about is to classify fish. You're given a real fish, and you have to decide whether it's salmon or tuna. How do you go about this? One way of doing this is you carefully identify features of the fish. You have a bunch of sensors that you have a tape and you measure the length and the color and everything. You get the best possible data because you hire people who are slow and painstaking with their feature extraction, and you build a perfect software architecture, and maybe you might even have to design a new learning algorithm that does something fancy for this domain. You implement it, you hope it works. And the advantage of this method is that you might end up inventing an entirely new algorithm that works perfectly for this, maybe a new learning algorithm, and this is roughly what we do in research. Another way is the hacker's approach. You do a quick and dirty implementation, you implement something using some data that you could find, and then you use all these diagnostic ideas that I just spoke about to decide whether you should go out, get more data, better features, fewer features, or anything, and you iterate. And the advantage of this is that it leads to faster release, and you can have like a somewhat okay solution much faster. You might not end up discovering something new, but you'll have a system that works. Not surprisingly, this approach works more often in academia. This one is more common in the industry. And there's no right answer. There is there's no clear consensus as to what's the right one. The problem with this approach is that you might end up optimizing too much prematurely, and the problem with that is the standard problem with greedy search. You might end up committing to a path up front that is not good enough, and you can't backtrack. So both are not good, both are good. It's often a matter of personality, which one works for you. It's and other such pressures which are external to machine learning. That said, in both of these things, there are a few things you should watch out for. Probably one of the most important and often overlooked things that you see is you do not have a good enough way of evaluating. You need to know what is success. Even before you start solving a problem, you need to know what is success. So for some problems, accuracy may be good enough. For some problems, precision, recall, and measure might be the right thing. For regression, for example, measuring accuracy or measuring whether you got the number exactly seems like a goofy thing to do. So you might have to define a square error or something like that. For more complex problems based on an application domain, you might have other things. So for instance, let's say you could measure the number of dollars that are lost because your classifier made a mistake. That's a perfectly reasonable evaluation measure that you probably really care about. And then, once you have an evaluation metric, you should ask yourself, does the loss function that you're minimizing actually capture that evaluation metric? The answer to that is more often than not, it is not. You end up making approximations. The other thing that you should be extremely wary of, and this is incredibly important both in research and in the industry, is you should be very, very, very careful that your data is not contaminated by you. Don't look at your test set. Your training set should not be contaminated by the test set. Don't let your classifier look at the test set. In fact, what I do, or what I try to do, is I encourage my students and my collaborators to compress the test data into a zip file, make it read-only, and not even look at it until I actually have to make the final submission for a paper, for example. Just so that I don't accidentally end up reading that data. The problem is contamination can happen in multiple ways. You could run an evaluation on your test set, and if you might end up evaluating on your test set just to know how your classifier is doing, and you see that it gets, say, 60% accuracy, and you look at a few examples that has an error to see what's going on, just a few examples. You look at those examples, and through you, the training set is contaminated because you look at those examples, you do some error analysis, you say that, if only I had this feature, it would work. You end up overfitting the test set. The problem with overfitting the test set is you can get excellent evaluation measures. You might end up getting, winning the competition, or getting your paper published, or selling your product better, but actually your classifier is not working. If you are actually selling the product, your customers are going to be unhappy. If you're writing a paper, your research is not going to be replicable. So, in fact, I would argue that contamination is very close to cheating. So it's kind of, it's borderline unethical, and please avoid that. And along the same lines, you should be extremely suspicious of classifiers that are perfect. Most real world problems are not perfect, and if you have a 100% perfect classifier, then you should look at it with suspicion. Let me give you an anecdote of contamination that led to a few people being fired. This was in the context of this ImageNet competition. By the way, everything that I'm saying is actually from a New York Times article, so there's no reason to hide it. This was in the context of an ImageNet competition. This is a bake-off that a bunch of people have to build classifiers to decide whether an image contains one of 1,000 category objects. And it's a very prestigious thing to win. To the extent that some companies started, and the way it worked was something like your Kaggle competition. People would write a classifier and label some data, upload their labels, and then they'll know how well they've done. And rightfully so, the competition had a limit of number of submissions per day, per team. So one company, which I'm not going to name, ended up creating 1,000 anonymous entries, 1,000 anonymous competitors, all of whom submitted slightly different predictions. And based on these, and now you get 3,000 pieces of feedback per day. And they built an online learning system using these 3,000 submissions. And not surprisingly, they won, because they basically ended up fitting the test set without actually looking at the test set. And eventually someone did some analysis and they found that there were 3,000 entries from the same IP address. Clearly that could not have happened. And that company ended up, it forfeited the place. Not only did it forfeit the first place, this became a nasty PR thing, and a whole bunch of people in the company who actually okayed this decision ended up getting fired. So, lesson here is overfitting the test set can lead to people getting fired. Yes?
So something that, I'm not sure if that runs afoul of your advice or not, but like, for example, for tuning hyperparameters.
Yes.
Starting with the assumption that the distribution is the same between test and
Right.
and training, I would look at both when it. I would be tempted to look at both when it comes to training, looking at hyperparameters about that have to do with like the shape of the data, but then it would wipe all my.
No. The problem is if you look at the test set, you have contaminated yourself.
But if you wipe away your weights and any leftover information about the data itself.
No, I would strongly advise against that. Don't even look at the test set. Of course, what I'm saying is a rather strong statement. So what I would rather prefer doing is for hyperparameter selection, you take your training set, divide it into two parts. You create a dummy test set internally, and you do your everything that you're doing on the little fake test set that you have created. That way, your classifier is only a function of your training set and not of the test set. It's dangerous to look at the test set. Even though you might convince yourself that you're wiping away all the information, you might inadvertently overfit the test set. And that's never a good thing. I saw your hand and then you. Yes.
So wouldn't that mean that as soon as you run your classifier on the test set and you see the accuracy, you're contaminated?
Unfortunately, that is true, and that's okay. Unfortunately, that's true, which means that you should try to minimize the number of runs on your test set and try to keep them towards the end of the final phase of whatever work you're doing. But the real problem with exactly that, the real problem that situation presents is, let's say you're done and you get some results. What next? Does this mean that you have to throw away the training set? Of course, that's the entire data set. Of course, that's not true. And in fact, another situation. Let me give you another anecdote here. One of the early data sets hand-created data sets that were created that in some sense changed the way people started looking at natural language processing was a data set called Pen Tree Bank. It's a collection of sentences and their parse trees. This was made in 1993. And this data is available if you are in a university. Basically, they took a bunch of news articles from the Wall Street Journal, annotated them with trees from all these articles were from 1989. In any case, they took the data, they split it into 3 sections, 3 parts. One collection is the training set, another collection is the development set, which is like the part of the training set that is allowed, that is visible to the, like this part that I was telling you about, held out set that the classifiers are not trained on but internally evaluated, and a third part called the test set. There's the official sanctified test set of the Pen Tree Bank. And in the 20 years or so that have passed since then, parsers, all statistical parsers that you know of, have at some level been trained on the Pen Tree Bank training set, cross-valid or hyperparameters chosen using the development set, and evaluated on the test set for 20 years now. So someone did a plot of, which means clearly as a community, the community is contaminated with the test set because people have looked at the test set. So someone did an evaluation of accuracy of parsers on the test set and the development set. If the classifiers of the parsers were actually truly representative, one would say that a parser that does this well on the development test set should do this well on the development set. It should be a straight line. What actually ended up showing up was they were all over the place. There seemed to be no correlation between the test set and the development set performance, which is a clear indication that as a community we have been contaminated by the fact that we've got one test set that everyone's been building on. So on one hand, you should try not to be contaminated by the test set. On the other hand, it's actually, as you work with the same data for a long time, it's actually impossible. So my advice is try not to look at the test set too much. And try to be honest with yourself. Try not to use any insight that you get from the test set to change your classifier. Yes?
So I just wanted to make sure I understood this in context. So if you're the one that is going and getting the data, then going and making the features, and putting all your data together, you already know what the test set is and everything.
No, you don't know the actual examples that are in your test set. If you're putting all your features together, you should do your this creative process of coming up with features should not happen in the context of the test set. So if I have a task, what I typically, let's say I want to invent a new task. What I typically do is I collect the data, shuffle the data, split it into train and test, and then lock away the test set, and then start looking at the data set. So there must be a sufficiently large enough collection of examples that are in the test set, and you do not look at the individual instances. You know the process in which the data is generated, but you do not look at the individual instances. Does that make sense? Alright. Also be aware of this trade-off between bias and variance, or between overfitting and underfitting. Some things like cross-validation help you trade off between these things and take advantage of these ideas. We spoke about the curse of dimensionality last class. Keep that in the back of your mind. Worry about it. There's not much you can do about it, but just be aware that intuitions that seem to work very well in 2 dimensions may not carry over to high dimensions, and there's nothing you can do about it. The only thing you can do about it is not to rely on proof by pictures, instead rely on algebraic proofs. Algebra does not change. We spoke a lot about theory, and I enjoy theory, but keep in mind that a theoretical guarantee might only be a theoretical guarantee, not in real data, because in order to get the guarantee, you might end up having to make invalid assumptions about the data. Like if you're a physicist and you want to measure the rate at which a cow rolls down a hill, you start assuming that it's a circular cow, a spherical cow. And be aware of these kinds of spherical cow assumptions. Sometimes your theoretical guarantees may be only true if you have infinite data, and we don't have infinite data, so Maybe the guarantees don't make sense. So the point is, as much as theory is important, experiments should really, on real data, should also play an important role in guiding your understanding of machine learning. And that's actually the real reason why every homework that you have had a theory component and an experiment component, because I don't think you can really, I do not believe you can understand what a classifier does until you implement it and actually let it do something on real data. We are in the world of big data, but unfortunately we are in the world of big unlabeled data. Labeled examples, labeled data sets are a scarce resource, a precious resource, and clean labeled data sets are like unicorns. It's very hard to get it, probably it doesn't exist. More data is always better, cleaner data is always better. So sometimes a problem that simply just doesn't work with 100 examples magically becomes perfect with 1,000,000 examples. And the only thing that changed was that you just had more data because classifiers got better. A classic situation where this happened was in the context of object recognition for computer vision. In general, for computer vision, all these things that you hear in the news with deep learning being awesome, one important thing that changed around the mid-2000s was that we started using the fact that the internet is pervasive to collect data. And suddenly we have massive amounts of data that we can do things. Massive amounts of labeled data. So the other thing that you need to keep in mind is that every time you use a learning algorithm, any learning algorithm, you have already made an assumption about some hypothesis space. Because remember, probably the very first lecture of this class, or maybe the second lecture, I pointed out that in the absence of any assumptions, learning is impossible. So you've already made assumptions about the nature of the problem, about a set of functions to search for, about features and all those things. So keep those assumptions in mind. Sometimes those assumptions that you injected into your task might stand in the way between generalization, you and generalization. For example, your data might not be linearly separable, and you're trying to fit a linear classifier, so it's not going to work. One place where this is crucial, and I keep talking about this all the time, is these assumptions come from some knowledge about the domain. If there is no magic in machine learning, and so if there is one and only one lesson that I want you to take back from this entire semester, I want you to remember that machine learning is not magic. It's just dirty math. Both dirty and math. So there is no magic, so don't fall for that hype. You can take advantage of any knowledge that you have about your domain to make your hypothesis better, and if you knew the insides of this beast, you can actually tweak it to be better. What kind of knowledge? Knowledge could include what model is the right thing for this task. Maybe for this particular task, you believe that the data is linearly separable because for whatever reason. Maybe a decision tree is the right thing. Don't end up committing to one thing and never be willing to change. So another piece of knowledge is sometimes choice of the learning algorithm could be some knowledge that you bring in. Does the data violate any fundamental assumptions that your learning algorithm makes? Every learning algorithm makes some assumptions about the nature of learning, about what you want to optimize. So you should keep in mind, but you should keep those assumptions in mind when you are employing the learning algorithm. For example, the perceptron algorithm, the vanilla perceptron algorithm, without any other changes, assumes or is guaranteed to work only when your data is linearly separable. So, in some sense, if you're using the perceptron algorithm, any linear classifier, you're assuming that your data is linearly separable. Maybe your data is not. Maybe it is. In either case, feature engineering comes in. Feature engineering is often the thing that most people doing machine learning spend most of their time on. We never spoke about feature engineering because I always kept saying it's a domain dependent thing. Instead of but there are some underlying principles that should guide your feature engineering. The idea of, for example, nonlinear transformations in order to get a higher, bigger expressive space. What you should realize is all of these things are implicitly a claim about nature, about the nature of the problem that you have. So if, for example, you were in the beginning of the Renaissance era and you collected data from an observations from a telescope about the positions of planets, and somehow you collect many such examples. If you had all the technology at hand, of today at hand, you could feed it into a learning algorithm and maybe discover laws of nature. Maybe discover the law of gravitation. Where, by the way, if you try to discover the law of gravitation, your features must be in the log space. If your observations are weights, the masses and the distances, and the gravitation constant would be the bias feature. If you don't know what I'm talking about, ignore it. One of the most common mistakes that I have seen even experienced practitioners of machine learning do, because it's just you forget about it, is to forget about the bias feature. If you don't have the bias feature, typically, and this is something that for example, I noticed even a couple of years ago, someone who's been doing machine learning for decades now, we were chatting about something and they had a classifier and it just did not work. They were unable to replicate a paper. And over the course of the conversation, we discovered that they forgot to add a bias feature, and that gave them a drop of 20% in accuracy. The accuracy went up from roughly about 69 to close to 90. That's 20%, yeah. And the only change they did was add one bias feature. Why? You should know the geometry of this thing, and the bias feature, not adding the bias feature basically reduces the expressivity of your classifier. Other advice generally favors simplicity. Learn simpler models first, but it's just a personal bias. If you like complexity, go for it, good for you. For me personally, I like simpler models first because if nothing, they at least form a baseline that I can kind of build more interesting things on top of. Ensembles seem to work well. In a lot of industry, a lot of times, people who are hired as data scientists in companies end up building ensembles. So random forests and such things seem to be the standard default thing that people try before thinking about something more complex. You should think about whether your problem is learnable at all. And by learnable, there is only one definition of learnable, and that is there generalization? After having seen a bunch of examples, can you generalize or distill that information into a new one? There are a few, because ML has become more and more prevalent, there are a few position pieces on machine learning and how it fits in the context of large software systems. There's some talk about how machine learning is the high interest credit card of technical debt. Why? Because you're committing to certain things and you're making mistakes up front because we're not aware of what's going on and treating it like a black box, magic black box. And hopefully, at least those of you here will not think of it that way, but these papers are both very interesting and you can check it out. In the broader context of things, I would really like to push people to start thinking about how machine learning actually matters. Beyond, simply predicting things like advertisements and making money from Google. This is a paper by Kiri Wagstaff, who was actually a Utah alumnus. She did her undergrad here a while back, and she then went on to do a PhD and now works for NASA's JPL. And she wrote a challenge paper to the greater machine learning community, and I think this is interesting enough that I'm actually going to read out each of them. Wouldn't it be interesting if a legal decision was made that relies on the result of machine learning analysis? What if there is $100 million saved because of improved decision making that is driven by a machine learning system? Machine translation is entirely driven by learning these days. Can we avoid conflict because of better translation? That seems like a really great goal. I don't know if that's even possible. Cybersecurity is important. Can we use machine learning ideas to help make our defenses better? Healthcare is extremely big and clearly important. Can we use machine learning to improve healthcare? The challenge here is a human life is saved because of diagnosis or intervention driven by a machine learning system. And this is already starting to happen. I don't know if any human lives have been saved, but definitely learning-based systems are starting to make a headway in, say for example, improving medical practitioner fatigue. Can we actually directly attribute a 10% improvement in human development index to a machine learning system? These are all grand challenges. These are not like, a class project. But you have a tool in your hand and you should think about how this tool might help something bigger. Let's just look back at the course. These are slides from the very first lecture. I started off by talking about definitions of machine learning. And my favorite definition was, and still is, this thing from Tom Mitchell, who said, a computer program is said to learn with respect to an experience E, with respect to a task or a class of tasks T, and some performance measure, a concrete, quantifiable performance measure P, if the performance in these tasks, as E increases, the performance increases. A very broad definition of machine learning that does not really care about whether you're using perceptron or a neural network. It's a broader class in the way it could fit like a way more than what we've covered in class. What we did see is we saw various kinds of models. We saw linear classifiers, we saw decision trees, we saw nonlinear classifiers, we saw ensembles. You should be able to, and in fact you implemented at least 3 out of these 4. We largely only focused on supervised learning, where the setting is there is an oracle that labels examples, and you have a collection of randomly chosen labeled examples, and you have to do what you can with it. But you should be aware that there are other modes of learning as well. Unsupervised learning is very common, and in fact it's becoming increasingly important because labeled data is very hard to get. Unsupervised learning is there's no teacher, there's just some unlabeled data, you have to do what you can with it. And semi-supervised learning is a sweet spot in between, where you have some amount of labeled data, tons of unlabeled data, and then you try to do something with it. And we did not cover unsupervised and semi-supervised learning, but the fundamental concepts that we looked at in this class might help you actually reason about something that you'll see in the future. We saw various kinds of learning algorithms in the supervised setting, and in particular one way of categorizing the learning algorithms we saw was online and batch. Online is a setting where the learning algorithm gets only one example at a time. We saw 2 algorithms of that kind, perceptron and Winnow. We saw many batch algorithms, naive Bayes, SVMs, logistic regression, decision trees, nearest neighbors, boosting, neural networks. All of these are batch algorithms. In general, all the loss minimization algorithms fit under batch. One of the most important things that we kind of skirted around, but also tried to express only mathematically but not practically, was the problem of representing data. If you have the right data representation, problem solved. If you have the right data representation, we know how to train a classifier. How do you get the right data representation? By data representation, I mean what features. And it's not a very, it's a bit of an art. Feature selection, feature invention is not something that we know how to do automatically yet. Neural networks are kind of going there, but it's still there's still a lot of manual labor involved. One thing that we did not cover at all, unfortunately, is this idea of dimensionality reduction, which says you have this massive feature space, you project it to a lower dimensional space using using a matrix, and you then learn the matrix. You figure out the matrix in an unsupervised way, basically. The classic method here is principal component analysis. You should take a look at this. There's some pointers on the class on the lecture slide, on the lectures page. We spent a lot of time thinking about the theory of machine learning. These are the laws of nature when it comes to machine learning, and in some sense we tried to define what is learning. We defined learning in 3 different ways: online learning, learning the probably approximately correct learning or back learning, and Bayesian learning. And all the algorithms that we saw would fit into these categories. It just so happens that learning as loss minimization is a practical technique that seems to transcend both Bayesian and pack learning, but that gives you a recipe for creating learning algorithms. You can think of machine learning, this table is from a paper by Pedro Domingos. You can think of any learning algorithm as having three components: a representation, an evaluation, and optimization. You can represent your classifiers. The first column here is what's your hypothesis space. Your hypothesis space could be nearest neighbors, or linear classifiers, or decision trees, or neural networks, or more complex things. You could evaluate your classifier in different ways. We looked at accuracy and precision and recall and the squared error, but there are other ways of evaluating your classifiers as well. And the third part is the search. How do you search your hypothesis space so that your evaluation metric, you get a high score according to your evaluation metric? In some sense, we only looked at gradient-based methods, but there are other gradient descent or stochastic gradient descent, but there are other algorithms as well. It just so happens that stochastic gradient descent has now become a dominant thing overall. But you could pick one item from here, one thing from here, and one thing from here. You might end up getting a different learning algorithm. You have all these possible choices, but I'm going to make a claim that maybe not all of you agree with yet. I'm going to argue that machine learning is almost too easy. I know. The thing is, there are a remarkably diverse collection of ideas. As you pointed out, the exam the sheet was rather dense. There's a remarkably diverse collection of ideas, and yet all of them seem to do pretty well, roughly well, equivalently in practice. So from an external point of view, machine learning is actually pretty easy. You just take an idea and you apply it. We did not cover a lot of things. We did not talk about unsupervised learning, clustering, hidden Markov models, or sequence prediction, multi-class classification, topic models, structured prediction, deep learning, and many more things. What we did see was the foundations of how to think about machine learning. And my hope is, based on this sort of new way of thinking, you can pick these things up more easily. If you're interested though, there are a few other classes that follow that might actually be interesting follow-ups of these ideas. Next semester we'll have a class on data mining by Jeff Phillips. We don't have a class on clustering every semester, but Suresh teaches that once in a while. I'll be teaching a class on structured prediction. Aditya is going to teach a class on theory of machine learning, and there are various application classes. So if you like this kind of stuff, you can follow up with other classes as well that cover some of these things that we did not see. This course, just to remind you, is focused on the underlying concepts and the algorithmic ideas. It's not about any one learning algorithm. I hopefully did not bias you by saying this one learning algorithm is always better than the other. It's not about one learning paradigm, it's about a way to think about learning. So what we saw was a broad range of theoretical ideas and good practical aspects of machine learning. Hopefully, you now have some confidence in your ability to implement learning algorithms. And maybe you don't have to implement learning algorithms in the future, but even then, if you actually take an existing implementation, you can reason about it and maybe make some tweaks to it so that it fits your problem. And a skill that kind of comes only by doing is that we did see a bit was get an idea of how machine learning can be applied or where machine learning is applicable in the sense of what kinds of problems are learnable and how to make the right choices with respect to algorithms, say with respect to supervision, with respect to models and so on. So I hope this class was useful. I definitely had a lot of fun teaching it because as I said, the class is large and extremely diverse. So thank you for the class, and I'll see you guys around.